Today we're going to do an experiment with alkali cyanides. We showed you our preferential way of producing these in one of our first ever videos, using sodium metal and anhydrous potassium ferrocyanide. What you end up with is a fused mass like this, which contains a combination of metallic iron and a mixed sodium and potassium cyanide salt. There's a small amount of cyanate and hydroxide impurity as well. There are other ways, but we've found that in order to do any sort of organic synthesis you need a fairly pure product, and it's difficult to get with other reactions. And yes, they're deadly. Take full precautions and don't even think about trying to kill yourself with them. It ain't pretty. So here's the starting material for making cyanide via this method. Anhydrous potassium ferrocyanide. It has to be absolutely water-free and anhydrous because otherwise the water content would react with the sodium and you'll get a product heavily contaminated with sodium hydroxide, which will be useless for most things. We had a great viewer question. Can you substitute ferrocyanide with potassium ferrocyanide for this reaction? Well, here's some anhydrous potassium ferrocyanide. It's an orange fine powder rather than pale yellow. So let's actually do it as an experiment and find out. So here we've got 10 grams of anhydrous potassium ferrocyanide. The reaction with sodium metal will be very slightly different, as you can see. This time we're going to need an extra mole equivalent of sodium metal as compared to the ferrocyanide reaction. So here we go. 1.8 grams of sodium metal. We've washed off the oil, so we'll first cut this up into small pieces. And we'll get these into a small porcelain crucible along with the ferrocyanide, and form a mixture. Okay, here we go. We'll use a burner and first heat this up to a low temperature, but enough to melt the sodium metal. Then we'll mix this into the powdered ferrocyanide thoroughly. Well, that didn't work out too well, did it? Sodium metal is a strong reducing agent. Ferrocyanide is an oxidizing agent. So it's kind of predictable, but at least it wasn't too violent. We let it cool and then add a few drops of water. Turns out that there's still quite a lot of sodium metal left in here as well. Dangerous, and not what we wanted to get from the reaction. So the answer is no. Ferrocyanide isn't going to cut it. There's probably some cyanide in there, but it's not going to be easy to get a pure product out. So let's recap the original process. We'll run through very quickly because you've seen this in a previous video. 20 grams of oven-baked anhydrous potassium ferrocyanide powder. 2.5 grams of sodium metal, cut up into small chunks. Sodium goes into the crucible. We actually recommend you use a metal pot instead for more efficient heating. Ferrocyanide powder on top of the sodium. And first we heat this to melt the sodium, then we'll mix the sodium into the powder carefully, and then once this is done we can commence the full heating and melting process. Once the stirred mixture turns a dark color, we're ready for throttle up. Risk of carbon monoxide and toxic gases, so get the ventilation on. The mixture will turn spongy and start to foam a little bit. And once it melts in about 30 minutes, you're done. Allow to cool completely, and protect from air if you can. Remember that this is now live and deadly. So from this point have a bucket of diluted bleach standing by, and full protective gloves on. And here's the solidified melt. This time we've got a product with a slightly spongy appearance, which is unusual. We think that heating in the metal canister is much better and more efficient for this reaction than the crucible. We've done an experiment to store this stored fused product as it is for 6 months in an airtight jar. We've done an experiment to store this fused product as it is for 6 months in an airtight jar. So let's take a look at that previous sample now. Here it is. We made this in exactly the same way 6 months ago, and then stored it. When we opened the jar there was a faint aroma of ammonia, but not much else apart from a subtle background aroma of HCN. It's got a yellow-brown coloration to it, so the iron produced in the reaction may have oxidized to its brown-colored oxide with the air present. But what we want to know, the million-dollar question is, how much active cyanide is still left in here? To find out, we're going to perform a reaction and see if we can convert the alkali cyanide present into a copper cyanide salt, copper 1 cyanide. Let's get our sample onto a hot plate. First we need to dissolve the water-soluble cyanide salts, and get rid of the insoluble iron and any other insoluble compounds. So here's 20 ml of water. We add this to the solid, and we'll see what dissolves. Some trapped gas bubbles. So it's dissolving in there. We'll get the heat switched on. We also roughly want to test the solubility of the soluble component, so let's see if we can make up a saturated solution. We've now only got a fine powder, so at this stage we'll filter the warm solution. We'll do this old school using a paper fluted filter. And we'll use another 10 ml of warm water to wash the beaker and the contents of the filter. And as the filtrate cools, we are actually getting little sugar-like crystals appearing. This is very roughly about the right solubility level for the alkali cyanide salts. Okay, so let's do the reaction and make the copper cyanide. The catch is that it's not as simple as adding copper sulfate to an alkali cyanide solution. If you do this, you get unstable copper 2 cyanide, which then decomposes forming deadly cyanogen gas. Not smart. So instead we do the reaction in the presence of a reducing agent, which ensures that the copper 1 cyanide is formed. So first up, here's our copper 2 sulfate. It's the anhydrous salt, although after a year in our possession has turned a very pale gray-blue color, as you can see. We're using 30 grams of this, which should hopefully be in excess of what we need to use to convert all the cyanide salts into the copper salt. And here's the reducing agent. 29 grams of sodium bisulfite. The expected reaction is shown on the screen, but we don't want to take chances with the dangerous side reaction, so this gives us a 50% excess on what we need. Let's just test on a tiny scale what happens when the cyanide solution meets the copper sulfate powder directly. A dark color, and cyanogen gas. This is not what we want to happen. So we'll watch closely when we do the reaction. So let's do it. First we've got a large beaker set up containing 200 ml of water and strong magnetic stirring. Copper sulfate first up. There's slight exotherm as the anhydrous salt dissolves, but the dissolution is quite rapid. Looking good. Now for the sodium bisulfite. We can dissolve this pretty easily in about 50 ml of warm water. Just a minute and we're there. And now we'll add a little bit of extra water to our cyanide solution, so that all the solids have dissolved. The dark color is interesting because the fresh product doesn't do this. This must be some sort of iron impurity formed in storage. We gently heat all the reactants until we're at around 50 degrees C. And then it's showtime. We get the copper sulfate solution stirring in up to about 60 degrees. Then the sodium bisulfite solution. This forms a green reduced copper complex. And then the cyanide solution. There's a white precipitate and a little foaming, but the bubbles seem to be sulfur dioxide. This dies down and then we leave the mixture stirring and heating for 15 minutes. There's a pale blue color, so this is a good sign that we had excess copper to start with, so should have conversion of all cyanide present. So let's filter this. We wash the beaker out with water. And then wash the precipitate with copious water. We finally dry the precipitate in the oven for 3 hours at 120 degrees C to get it completely dry. And here's what we're left with. A lumpy but dry cream-colored solid of copper 1 cyanide. It's fairly dense and we've got 8.4 grams of product here. We know we started with 13 grams of the solid melt, and this in theory contains around 7.3 grams of mixed sodium-potassium cyanide. So we can calculate our theoretical yield of copper cyanide based on this and compare. And it turns out that our yield on theoretical is just under 50%. This is interesting because it suggests that we've lost a fair bit of product in storage. Possibly to hydrolysis or decomposition, possibly through some reaction in contact with the iron and iron oxides formed. We probably did also lose some in the initial filtering process as well though, so next time we'll have to try this again using freshly prepared melt, and maybe dissolve out the cyanide and extract more efficiently to see what the fresh yield is. That will have to be a job for our next series in the future. Still a few more interesting videos for you though, so stay tuned.